Dafür Molar.
Okay, so let's try to go a little more quickly. You don't find this too quick, too slow, too fast? Whatever. Okay. All right, so del du is equal to Q plus W. In general, Q and W depend upon the path, but of course if the volume is constant, if I write del du at volume constant, if the volume is constant, then there's no expansion work. So if we have no expansion work and no other work, then del du is equal to Q. So del du is independent of the path, remember, so if you can measure the heat for a reaction at constant volume, it's independent of the path. Okay. Right. And this is how we measure heats of reaction. We generally use what is called a bomb. Well, it's not the only way to do it. One way to do it is use a bomb calorimeter. A calorimeter is a device to measure heat. There are different kinds of calorimeter. A bomb calorimeter, I'm greatly simplifying the thing here just to show the principle, but in a bomb calorimeter you're trying to measure the heat of a reaction at constant temperature, the internal energy change, so you want to keep the volume constant. So del du at V is Q at V. So what I do is here I take a calorimeter. This is a very, say, large vessel, and let me simplify to make it filled with water, say many liters of water. You probably wouldn't want that for reasons that will become evident, but let's say it is anyway. And this is insulated from the surroundings, so it's a big insulated vessel, and it's fitted with, trying to get the principles here, fitted with a thermometer. All right, there's your thermometer, and the thermometer measures the temperature of the water. Okay, and the water starts out at 25.00 degrees Celsius. Okay, great big bath, and you measure the temperature very accurately. And now what you do is you take the bomb, and the bomb is a steel cylinder. So here's your thick steel cylinder with a screw cap. It's a steel thick. And then here you put your reaction. Let's say you want to have carbon plus oxygen going to CO2. You want to measure that. So you put a bunch of carbon and oxygen in there, an excess of oxygen, say, so that it goes very quickly. And you would put, say, a little spark plug or a little wire in there. You get the whole thing set up with your carbon and oxygen. You pass a current, you ignite this, there's an explosion, and the thing reacts completely to form CO2, and there's a change in internal energy. The heat gives off a lot of heat. The thing starts off with U1. The initial state was 25 degrees Celsius. Now, the intermediate states are very complicated. It starts to heat up, it goes up to very high, inside the system it heats up to high temperature, the pressure gets huge. Doesn't matter. You wait till the thing's cooled completely back down. Well, not quite 25 degrees, because of course it's going to heat the water up a little bit. But afterwards you measure the water at the end, and that was the initial temperature of the water. Afterwards you measure the temperature of the water, and it's 26.23 degrees Celsius. Because all the heat has been transferred to the water. So now your system is essentially back in its initial state. Well, give or take a degree, you can always make a slight correction for that. So the energy transferred then is the energy that's been transferred. Now that the final state is back at 25 degrees, the del du is equal to Q. And you measure the Q. If you know the heat capacity of the water in the calorimeter and you know the delta T, you can calculate how much heat went to the calorimeter. Okay, so del du then is CV of the calorimeter times 26.23 minus 1. Okay, so the calorimeter measures how much heat was transferred. The final state of the system is essentially the initial state. The slight difference here you can make a correction for. So you measure the heat of the reaction at constant temperature and essentially at a constant volume, and that's equal to del du, and that will be independent of anything that happens in between. Okay, that's why you do it this way, because del du is equal to Q. Q in general is not a state property change, but in this particular case, at constant volume it is. So that's how you measure. And then these can be put in tables, and that's how you measure the internal energy. Unfortunately, in the real world, reactions don't occur generally at constant volume, they occur at constant pressure. Okay, and that's harder to measure. How would you measure the heat at constant pressure? You'd have to have this thing in a container at constant pressure, but I mean that would be crazy because the thing would be flying. Okay, so measuring at constant volume. So a bomb calorimeter measures del du at constant volume. Okay, so let's now go to back here. Back to the number 42, I guess it was. I'm going to go down a bit. I'm going to skip the second law for a moment. And I'm going to go down to section 2.2, enthalpy, page 9. Is it up?
Sorry, delta U is equal to CV.
Of the calorimeter. What you're doing is you heat it times delta T. So the heat that's caused will be equal to the change in temperature of the calorimeter times the heat capacity of the water, which you have to calibrate, of course. You have to calibrate the calorimeter. That's not the CV of the material, CV of the calorimeter. Now the final, so then you measure delta U from going, what you've measured in that case then is Q, what you've measured is equal to delta U for the reaction, carbon plus oxygen at 25 degrees gives you CO2 at 26.23 degrees, which is, for all intents and purposes, 25. And you've measured delta U of that reaction by keeping the volume constant. Okay, now, enthalpy is a state property defined as H is U plus PV. That's a definition of H. Enthalpy comes from the Greek word for heat. Consider a closed, now, U and V are state properties, so H is a state property. Delta H is independent of the path. Obviously, PV and U are. So H is just another property of the system. It's not a new property, it's just a sum of old properties. So why do we define it? We define it because it's useful. We'll consider a closed system undergoing a change of state. Although the overall process may be reversible, we assume that any work of expansion is approximately reversible. So I'm having a system that's undergoing a reaction that's expanding somewhat. We assume the expansion is more or less reversible, even though what's going on in the system could be an irreversible reaction. That is, the external and internal pressures are for all intents and purposes equal. And we're assuming further that there's no work other than the work of expansion. I've seen these equations applied to, say, the heat and so on going on in an electrical cell, electrochemical cell, and this is wrong, because in an electrochemical cell, you have electrical work. It doesn't work at all. So I've seen actually papers written making the whole thing wrong. You got the assumptions anyway. So du is dq minus pdv. So du is dq plus dw. The reversible work is minus pdv. We're assuming the work's reversible. It then follows from the definition of H that dH is dq plus vdp. Yes. Well, you differentiate. dH is du plus pdv plus vdp. Okay, put that equation into this equation, and you end up with this equation. Furthermore, if the pressure remains constant, then dH is equal to Q. So we had, if the volume remains constant, the internal energy change is equal to the volume change. Now we have shown that if the pressure remains constant, the heat at constant pressure is equal to delta H. Now this is very interesting because this means again that delta H now is a state property. So QP then is equal to H of the final state minus H of the initial state, and it's independent of the path. So if you can measure the heat, so the heat of a reaction at constant pressure is independent, or the enthalpy change of the reaction at constant pressure is dependent only on the initial and final states and is independent of the path. And this is really good news because when we carry on chemical reactions, or most reactions, we're carrying them on at constant pressure. Okay, now if the heat change for a chemical reaction depended on the intermediate states and all sorts of details, you'd never be able to do it. But the heat of a reaction depends only on the final and initial states at constant pressure. So this is why we define enthalpy. And in fact, since it's so important, I mean, most things are carried on at constant pressure. People talk about the enthalpy as being the heat of the reaction. Actually, it's not the heat of the reaction. U could be the heat of the reaction if it's a constant volume. In general, it's not the case, but at constant pressure, H is the heat of the reactions. When people talk about the heat of a reaction, they usually mean H, but to be strictly correct, they should talk about the enthalpy. I will say heat, but I mean enthalpy. So this is extremely important because it means it's independent of the path. Okay? So the enthalpy change of a closed system and passing from initial to final state at constant pressure is equal to the heat exchange with the surroundings, as long as you're assuming the PV work is more or less reversible. Generally, the PV work is not that big a thing anyway, so this isn't such a major issue. But it does only apply to the case of only PV work, so if you're applying it to electrochemical processes, it isn't true. This is an important result, as I just said. As an example, suppose the initial state of the system is 1 mole of carbon, 1 mole of oxygen at 298.15 at 1 bar pressure, and the final state is 1 mole of CO2 at the same temperature and pressure. The enthalpy change of this reaction then is written as delta H 298 is minus 393. And where the the superscript 0 up here means that this is the standard state reaction. Why don't I put the screen down? Means this is the standard state reaction involving pure solid graphite. Standard states then, unless otherwise defined, the standard state of a gas is the gas at 1 atmosphere pressure. It's not quite right, it's on the extrapolated line from 0, but let's not get into details. For all intents and purposes, at 1 bar pressure. The pure gas at 1 bar pressure. The standard state for a solid or liquid is the pure solid or liquid. Standard state, however, just talks about the state. If it's pure material and the pressure is 1 bar for the gas, what it means is the pressure of the gas is not different. Partial pressures are 1 bar, and the carbon is pure. If the carbon were in solution, it would not be in the standard state. The standard state has nothing to do with the temperature, however. You can have the standard state to be at any temperature. You can have a standard state at 75 degrees. Standard state of carbon is just pure carbon. Okay, this is a reference. 298 is not the standard state, it's just a reference temperature. Okay, it's not the standard state. Hence, an exothermic heat will be observed. The delta H is negative, so heat going out of the system is negative. So negative heat means an exothermic reaction will be observed independent of the reaction path. So it doesn't matter about the intermediate states. If I take carbon and oxygen and I burn them, and you form a flame and you get a huge amount of, the thing gets hot, and the carbon and oxygen are being heated as they're burning, and then they cool back down. When the CO2 is cooled back down to 25 degrees Celsius, the total heat will be 298.15, independent of anything in between. Okay? So for instance, during the combustion, the reactants may attain high and unknown temperatures. However, once the CO2 is cooled back down, the total heat which has been exchanged with the surroundings will be 393.52, independent of any intermediate temperatures. So that's what delta H is all about. Now, we generally then, this is what you find in tables. You find the delta H of chemical reactions at 298 degrees are in your thermodynamic table. That's what is stored in thermodynamic tables. That's what's stored in FactSage database as well. The delta H for various reactions, many of which have been measured calorimetrically, although there's other ways of doing it as well. And they're tabulated at 298, simply because that's a convenient reference temperature. We can make corrections, as you'll see in the homework problems, for different temperatures. And they're tabulated in the standard state, again, because we need to be talking about something everybody knows what we're talking about. We're talking about pure solids, and liquids we're talking about gases at 1 bar partial pressure. Now clearly you cannot tabulate the enthalpy delta H for every possible chemical reaction, because the number of chemical reactions is equal to infinity. Okay, but then we can use again the fact, you know, I always lose that brush. We can use the fact that the enthalpy is a state property, and we then end up using what's called Hess's law, which I'm sure you all have seen, but let's say what we generally tabulate, you generally find in the tabulations and in FactSage is you find the tabulation of the enthalpy of formation of a compound. The enthalpy of formation of a compound, by definition, is the enthalpy of the formation of the compound from the elements. So if we say C plus O2 equals CO2, that in this example here, this is the enthalpy of formation of CO2 at 298.15. At another temperature, it'll be another enthalpy. It'll still be the enthalpy of formation, but at another temperature. But the enthalpy of formation is from the pure elements as reactants in their standard states. So, and they're standard and most stable states. So the most stable state of oxygen is O2, not O3 or O monatomic. The most common state, stable state of carbon at 298 is graphite. Well, actually, yeah, it's graphite. Okay, so carbon plus O2. So that's what we mean by formation. So we could write the reaction CO plus 1/2 O2 equals CO2, and then you're forming CO2, but this by definition is not the heat of formation because the reactants are not elements. Okay, so you're forming CO2, but this is when people say the heat of formation, that's what they mean from the elements in their most common states in their standard states and the most stable standard state at the temperature required. So now I would have, say, PB plus 1/2 O2 equals PBO, and for that I'll have a delta H. Again, the standard up here means it's a standard state reaction, so that's delta H for reaction 1, which I'll find in my thermodynamic table. And let's say I have titanium plus oxygen forms TiO2, and my thermodynamic tables, I'll find the value of delta H2 for that reaction, all at the same temperature. And now if I'm interested in a reaction such as, say, PB plus TiO2 forms 2PbO, PbO plus Ti. And I'm interested in what is the delta H of that reaction. Now, so if I look at this, so that's delta H3. Now this reaction here I will not find in my tables, but delta H1 can be written as the enthalpy of PbO minus the enthalpy of Pb minus 1/2 the enthalpy of oxygen. Or now I'm using the small h to indicate that these are molar quantities. And this means 1 mole, this is the enthalpy of 1 mole of PbO in its standard state. Although we do not have absolute values of these, like a real absolute value, as I said, it doesn't matter because we never really care about the absolute value, we only care about the difference. However, you will find a convention in the literature. It's only a convention, it's an arbitrary zero. The arbitrary zero is that the standard enthalpies of elements in their most stable state at 298.15 Kelvin is 0. Okay? So the delta H for 1 at 298.15, then by convention is equal to the absolute enthalpy of PbO minus 0 minus 0. Okay, so this is just a convention for purposes of tables. The enthalpy of an element, not a compound, the enthalpy of an element at 298.15 Kelvin in its standard state, in the most stable standard state, so this would mean solid lead, pure, and oxygen gas at 1 atmosphere, is equal to 0 by convention. And in that case, we can say the enthalpy of reaction 1 is the enthalpy of PbO. But it isn't really, it's really the difference. Okay, I'm just trying to point out so when people talk about it for a second. So it's really, let's go back to this though, not using the convention, you don't have to use a convention, it's really the difference of PbO minus Pb minus oxygen. Delta H of reaction 2 is the enthalpy of TiO2 minus the enthalpy of titanium minus the enthalpy of oxygen. And you will find that delta H of 3 is equal to the enthalpy of titanium plus 2 times the enthalpy of PbO. Remember, the enthalpy, the delta is always the enthalpy of the products minus the enthalpy of the reactants. So delta H3 is the enthalpy of the products, PbO and titanium, minus the enthalpy of lead plus the enthalpy of TiO2. So it's the enthalpy of the products minus the enthalpy of the reactants, the same thing I did here. Delta H1 is the enthalpy of this reaction is the enthalpy of the products minus the enthalpy of the reactants. Here it's the enthalpy of the products minus the enthalpy. Everybody cool with what I'm doing? And then I think if you just look at, you compare these equations, it's very clear. Then the delta H3 is equal to 2 times delta H1 minus delta H2. So in other words, you don't need to tabulate delta H3 because it's equal to twice the energy for reaction 1 minus the enthalpy for reaction 2. Or, when you look at this, then it's very simple that the delta H of any reaction is equal to the sum of the enthalpies of formation of the compound products minus the enthalpies of formation of the reactants. The enthalpy of formation of an element being 0. Okay, so you write any reaction, so what you can simply say, I'll look at this reaction right off, and I say the enthalpy change for this reaction is 2 times the enthalpy of formation of PbO, plus the enthalpy of formation of titanium, which is 0, minus the enthalpy of formation of TiO2, minus 0. So you don't actually need the convention, you just, it's the enthalpy of formation. Or, if you like, you can say it's the absolute enthalpy, 2 times the absolute enthalpy of PbO, minus the absolute enthalpy of TiO2, where by convention the enthalpies of the elements are 0, but it comes out the same thing. And if you look in the FactSage database, you will in fact see that we use the convention. So in the FactSage database, you will see that H naught of lead at 298 is in fact 0, but it's just a convention. That's called Hess's law. Okay, that simply states that the changes of the enthalpy changes of chemical reactions are additive like linear equations. Now this clearly applies then not just to H, but it applies to any state property, like delta H1 is H of the final products minus H of the initial products. But I mean delta U of 1 is equal to U of the final products minus the U of the initial products. So Hess's law would apply to U's. Delta U for this reaction would be the internal energy of formation of the products minus the internal energy of formation of the reactants. Or the internal energy, okay. Would apply to entropy, to Gibbs energy, to volume even. The change in volume of this reaction is equal to twice the change in volume of this reaction. Okay, any state property, not an intensive property. It doesn't apply to temperature, doesn't apply to pressure, obviously, but it applies to H, U, S, V, G.
Sir, the internal energy of the elements are equal to 0 also.
No, it's only the enthalpies for which the. Okay, if you applied this for delta U, it would be the entropy of formation of PbO. Well, the internal energy here, you'd have to have an internal energy. You would have to sum up the heats, the actual absolute values. All right, I see what you got. What I said is true, but it's kind of less than useful. Okay, it applies to the entropy. It certainly applies to G. Okay, you're going to get in a little bit of trouble if you... What I said is true, but you're going to get into trouble if you look at it that way. Wait till I get to the entropy, you'll see how we do this with the entropy. Okay, enthalpy is where you're really interested in enthalpy works out. The others too, but then you have a little bit of trouble with what you mean by the entropy of titanium and lead, and that has to be. Yeah, okay. So he's right, forget what I said about that for the moment. Just assume for the moment we're talking about enthalpy. Okay, but this is how you do it. So this means you don't have to basically then, you have to tabulate the enthalpy of formation of every compound from the elements, and then you have a complete database. Right. For enthalpy. Okay, if you plot the enthalpy of formation of every compound from the elements, you then have a complete database for calculating the enthalpy of any reaction at that temperature. To go to other temperatures, you need the heat capacities. We'll get to that. And this all goes back to the fact that H is a state property, and it's the enthalpy, it's the heat at constant pressure. Okay, now here's the problem with this text. Since I haven't actually published it yet, the figures are all at the end. It just occurred to me. Okay, figure 8 is the standard. Well, I should put these, I'm going to have to put these in a separate file, aren't I? Otherwise I'm going to be going back and forth.
Oh, you can give a separate file.
Yeah, we're going to have to make the...
I already have
Okay, I don't have it here though. Okay, I should have done that. I didn't think of that.
it.
Okay, so let's talk about the enthalpy of heating something. So we'll go to figure 8. Figure 8's down at the end. And I bet some of them are going to be sideways too, right? We're going to have to talk about this. You need to get this straight. All right, so I haven't thought about that. Yeah, I'll have to look at that sideways, I guess. Sorry about that. How can I, there's no way I can make this any better, can I?
I think you can go
Yeah,
document,
so-
rotate
I
page.
can rotate
There's a
it somewhere.
rotate.
Where do I rotate?
Maybe to
Document, I
view
think.
or something.
Sorry?
In document.
Or document or view.
Yeah.
View. The next left. Not
Rotate
view.
view. Clockwise. There we go. I have to make it bigger now. All right. Okay. Next course, this will be better. Okay, but now I can't be reading the text at the same time. Now where's the text here? Okay, this is the graph of the enthalpy of you read it up here, standard molar enthalpy of iron. Okay, so this is for 1 mole of iron, and it's the standard enthalpy, so it's the enthalpy at for pure iron. At 1 atmosphere, actually. I say the standard state for a gas, it's an ideal gas at one bar. For a solid or liquid, it's the pure solid or liquid, and to be strictly correct, it's also under a pressure of 1 bar, which doesn't matter much for what we're doing here, but if you're a geologist and you have iron under a pressure of a couple of gigabars, then it does change its enthalpy. Okay, so this is the standard enthalpy of iron. So this is the H, the 0 means standard. So this is the standard enthalpy, 1 mole of iron at a temperature T, minus 1 mole of temperature at a temperature 298. So the process is iron at 298.15 produces iron at T. The pressure is constant, so the heat is the change in enthalpy. So the y-axis then is simply the heat required to heat 1 mole of iron at constant pressure from 298 to whatever temperature you're dealing with. Okay, so you start here at 0 at 298, and then you heat the material up. The slope of this is the heat capacity. Okay, the heat capacity in general, the heat capacity is defined as dq dt. It's the heat you add to heat the thing up. Okay, if you're dealing with a constant pressure process, then the heat capacity at constant pressure is dH dt, because at constant pressure, Q is equal to H. So Cp is the heat capacity at constant pressure, so it's dH dt. If you can also have a heat capacity at constant volume, which is the heat at constant volume, which is du dt, and there was a difference. A big difference when you're talking about gases, a small difference when you're talking about solids and liquid. Why is there a big difference when you're heating a gas up? Heat capacity of a gas at constant pressure, the heat capacity of a gas at constant volume. Which is bigger and why? Okay, when I'm heating a gas at constant volume, so let's imagine here I have, again, this is my old cylinder with the piston, here I have the gas, and I keep the volume constant, and now I heat it. I add heat. So what I'm doing is I'm adding internal energy. Okay, but supposing I do it at constant pressure. Now if I heat the thing at constant pressure, what happens is I'm also lifting up the piston and doing work. So now when I heat up the gas, not only do I have to supply internal energy, I also have to supply energy to lift the piston up. So I need more energy. And it's quite a bit more. Okay, so the heat capacity at constant pressure is greater than the heat capacity at constant volume. In fact, there's a little thing for you to work out at home from the ideal gas law. Okay, what is Cp over Cv? Or Cp minus Cv for an ideal gas is what? Yeah, okay, but RT, but, or R, actually, but 3 halves R. But it's significant, it's big, because you're supplying heat not just to increase the internal energy to make the molecules move faster, but you're also got to lift this thing up. In the case of solids or liquids, well, it's the same thing. The solid's expanding a little bit against the atmosphere, but the change in volume is so small that it's trivial. Okay, so heating up a solid or liquid. Cp is also bigger than Cv for that reason too, but it's a minuscule amount because the volume change is so small, it doesn't really get very much from the expansion. However, CP for a solid, CP and CV for a solid are in fact can be significantly different, but not for that reason. For gas, it's simply because you're expanding against the external pressure. For a solid or a liquid, it's because the bond length is changing. Even though the bond, if you heat a solid, the bonds are getting longer. Okay, and even though it's not very big, the bond energy has changed quite a bit, even though you make a very slight change. Okay, so if you take a solid and you constrain the volume and then heat it, okay, the bonds are remaining at a constant length. If you heat it at constant pressure, the bonds will expand. It's going to change this is going to change the energy of the system, and you get a difference. Not as big as this, but you'll get a difference. The difference actually in the gas, the heat CP can be different by about 10, comes up to about 10 joules per mole. In a solid, it might be of the order of 2 joules per mole. The reasons are different. Anyway, the heat capacity varies with temperature, and this line is not a straight line, so CP is the slope of the line. CP is dH dt. So the heat capacity is the slope of the line, dH dt, and it varies with temperature, because as you heat the thing up, the bonds get further apart, the system changes, the vibrational energy levels change, and the curve is different. This tends to be, to a first approximation, these things don't change very much with temperature, but they do. And they also tend to increase the slope with temperature as the tendency, although it can go the other way in certain cases. Okay, then you okay, so I can write now the heat capacity is also a here I wrote the heat capacity as du dt, and that's supposed to be an uppercase C. I could write a lowercase c. This is a small c because it means molar is dH at constant pressure dt, and the units are joules per mole Kelvin. That's the molar heat capacity. Heat capacity is an extensive property. It takes twice as much heat to heat 2 grams of something as it does to heat 1 gram. And I can also write then that H at some temperature T1 minus H, say T2, minus H at some temperature T1 is the integral from T1 to T2 of Cp. Here we have iron melts. This is the melting point with Tf, we have F for fusion. I write T0 because it's the standard temperature of fusion, meaning under 1 atmosphere. If you change the pressure, you're going to get a different, but not much. Generally the rule is maybe 100 bars can change the temperature by a degree. It's a general rule of thumb. This is a first order phase transition. First order phase transition means it occurs at constant temperature. Okay, so the iron at constant temperature goes from solid to liquid as you supply heat. And this is the amount of heat that you supply, and that's called the heat of fusion. This is the standard heat of fusion, standard because it's one pure material. Most standard molar heat of fusion at the equilibrium melting point is 13.807 kilojoules per mole. Okay, and this is heats of fusion are always positive because they are for the reaction solid goes to liquid. The liquid always has a higher heat than the solid. Okay, and that's kind of typical for the heat of Now you also have 2 other first order phase transitions. In iron you have a first order phase transition as the BCC alpha goes to the FCC gamma. This is T naught alpha gamma, and this is also a first order phase transition with an enthalpy 1184.8 Kelvin is the temperature of transformation. And I didn't plot them on here, and this is for the gamma going to delta for FCC going to high temperature BCC. You can see a very small first order phase transition. The reason it's smaller than the delta H of fusion is because it's a smaller change in the atomic structure. Just changing the atomic structure from BCC to FCC does not involve such a big change in bond energy as breaking the whole thing up to form a liquid. Okay, so general rule of thumb is you'll find the enthalpies of fusion are about of the order of 10 times the enthalpies of fusion of solids, from solid state transformations. I mean, by no means is it 10, it could be 5, it could be 20, but it's of that order. Okay, because it's a much less drastic change of bonding. If you were I extrapolated this up and you went from liquid to the gas in 1 atmosphere, it would be about 10 times that, because that's a complete breakup of the whole system. So for, I don't know, the heat of fusion, the heat of vaporization will be of the order of 150, 160 kilojoules per mole. That's just rule of thumb, but we'll come back to this again later about how you can estimate some of these things. You also can have changes which are second order phase changes that do not involve a change in, we'll talk about this sometime here, at the Curie temperature where the thing goes from ferromagnetic to paramagnetic. There will be almost a change in slope of the heat, but there's no discontinuity in the heat because there's no actual phase change in terms of nucleation and growth. Okay, so this is a second order phase transition. So the slope will change, not quite abrupt. Well, you can argue whether it changes abruptly. If the slope changes at the Curie temperature, if you want to blow this up, you would have the plot in this graph. You go up like this. And this is the Curie temperature here. Okay, this is the H curve. Okay, so there's no abrupt change in H, but there's an abrupt change in the slope. So if I were to plot CP, the CP goes like that. Well, actually, I'm going to do it like this. So there's a change in CP, there's a change in slope actually it goes down. It actually goes down and it drops. Okay, there's a change in slope, but no change in H. That's called a second order transition. And what's happening is the CP, the spins are becoming disaligned. They become completely disaligned at this point. But first order phase transition means constant temperature phase transition. Okay, how do you measure the enthalpy curve? How did this experimental curve, how do you obtain it? What kind of calorimeter would you measure that in? Measure the heat, so it's a calorimeter, but you would use a drop calorimeter. The way you do a drop calorimeter, here's your calorimeter. Again, I'm simplifying, you would not want to ink it out of water, but let's say you made it out of water. So here you have a cork in here. Here you have your big, same thing, big bath of water sitting down there, insulated from the surroundings. There's the thermometer sitting in it. Same. Okay, let's say we use the same calorimeter as we did for the bomb calorimeter. Okay, so this is a big bomb water sitting here at 25 degrees Celsius, and you're measuring this great big volume. Up here you have a furnace. So here's your, say, electric furnace. Your tube, and inside that furnace you put a little glass ampoule or some sort of an ampoule containing your iron, and it's suspended from a cord up here, and this is at T. Temperature not 25 degrees. So this is your electric furnace. You keep this thing up at 25 degrees. Okay, so it has a certain heat, HT. Then at a certain moment, you remove the cork, you cut the cord, this thing drops down into here to plug back in. You assume that there's no heat loss during the fall, or you correct for it. Then when all this heat has been transferred, this thing then, the iron then cools from T to 25 degrees, and you measure again, this goes to 26 point now, whatever, and you measure the heat transfer. And that is HT minus H298. Now, of course, the water's not going to work because it's going to evaporate and explode and everything, but there's different ways. Generally, you would make this, I've seen these made out of a very large block of aluminum. So what you do is you actually have a hole in the aluminum with, say, some gold turnings here, so the thing doesn't bust when it hits the bottom. And this has to be a much more elaborate system of baffles, and you have things here, but the principle is the same, and the aluminum then would have a thermopile, maybe 50 thermocouples in series, so that you can measure the temperature of the aluminum very, very accurately to 100th of a degree, and it's the same. Okay, so what you measure is you measure HT minus H298. That's called a drop calorimeter because you drop the calorimeter, shoot. All right, so what you do then is you measure one point on here. So you have to repeat this many different times, and you essentially measure points on the diagram. How do you measure the heat of fusion? Well, you measure the heat of fusion by basically measuring points on the curve above and below. So you've got here's your H curve, T, and there's your melting. This is the solid and this is the liquid. By dropping the calorimeter, I measure HT minus H298 at several points here. I measure it at several points here. I extrapolate this line, I draw a vertical line at the melting point. Melting point has to be measured in a separate experiment. Okay, so I extrapolate this line to the melting point, and this then is my diffusion. So that's the drop calorimeter principle. Sounds very simple. Actually, calorimetry, the principle of calorimetry is extremely simple. Trying to build a accurate calorimeter is an extremely complex thing to get it accurate enough. Calorimetrists devote their lives to building accurate calorimeters to get rid of all these little possible problems which are enormous. Anyway, that's the principle of a drop calorimeter to measure. This is called the heat content of iron curve. It's actually the enthalpy curve. 298. Another way you might measure the heat. Then how do you get the heat capacity? Well, you get the heat capacity, you measure the H, and then you join the thing up, you fit it up to a curve, and the slope is the heat capacity. Since you're not measuring the heat capacity directly, it's only the slope of a bigger property. This does not give you a highly accurate heat capacity, of course. Another way to measure the heat capacity is to use what is incorrectly called an adiabatic calorimeter. But in the adiabatic calorimeter, you would then take this is your electric furnace. Let's say you take your electric furnace at T, and so you would have your sample. This is your sample in here, in an ampoule in the furnace, which is being kept at some temperature T. Then around the sample, you have another electrical turning, okay, and you apply a certain amount of energy for a certain time quickly. You use certain voltage and a certain current for a certain amount of time, so you've supplied a certain amount of electrical energy, which has heated this from T1 to T1 plus delta T, and you measure delta T by putting a thermocouple in the sample. Okay, and then CP would be the delta. Your electrical energy would be W, you put W over delta T. You measure the heat, you actually supply heat, and you actually measure how much heat it requires to heat this from 1000 to 1001 degrees. Of course, you're losing heat, it's not really adiabatic, but you would try to, and this is complicated too, you maybe put your thing in another container that's semi-insulated so that you don't lose too much heat, or you make corrections for it and so on, but you're trying to actually measure, you keep the thing at temperature, then you add electrical heat, and a certain amount of heat, and you measure how much heat's required to raise it by a degree. Then again with all sorts of experimental corrections, but that does give you a more accurate actual slope at that particular point. But that's your adiabatic calorimeter. Okay, well, it took a bit longer. All I talked about is the first law, really, energy, heat, and this kind of stuff. So I'm going to give you some problems to do before Tuesday, and see how you. Well, it should be straightforward. The course will get less trivial as time goes on. I'm going to talk about the second law of thermodynamics next Tuesday, the concept of entropy. Then we'll move on to Gibbs energy, chemical potential, the phase rule, and then we'll get into the solution theory. Okay, I think it's necessary. These are simple concepts you've seen before, but to really understand the things, you got to make sure you've really got the fundamental understanding. Any questions about the material? Okay, so for Tuesday, for the homework problems, take a look at, as I said, these problems. Make sure you understand them. If you don't, then by Monday you'll have the solutions on the website, so you can look at those. And then on Tuesday, if you have any questions about them, you can ask them. So this will be section 1, 2, questions 1 to 6 inclusive. And that's on first law and ideal gas equation. Section 2, which is on the enthalpy, heats of reactions. 1, 2, 3, 4, 5, and 8. And you can read in this book we're dealing with here, the next 2 or 3 sections, the whole section on thermodynamics at the beginning, on section 2 on second law, then the Gibbs energy and so on. I'll be going through that more or less in the next couple of weeks with examples. I'll try to get these figures organized better. Okay, thank you for your attention. Next Tuesday, 1 o'clock. Here. Ready? 1, 2, 3, stop.